Perfecto. Ya le van a estar. Good morning, everyone. It's my pleasure to present our today's speaker, Junbo Zhang. She's visiting us for more than 1 year and a half already. She's assistant researcher working in the Chinese University of Chinese Academy of Science, where she also serves as astronomer in Xinglong Observatory. In her main interest in astrophysics compasses the study of stellar physics, elemental abundances, stellar parameters. She is specifically devoted to calculate NLTE departures, thermodynamical equilibrium calculations that have a wide range of applications in stellar physics, the chemistry of the complex assembly process of the Milky Way, supernova yields, and many other applications. So any of you may be interested, specifically people working in stellar physics, I think she's very keen to offer her knowledge on that. Now she's based in the library, so downwards. Yeah, I think she will tell us today about her current project working with Carlos Allende and also Jonah and myself. So Junbo, thank you so much for being here. Floor is yours, and I'll give you a 5 minutes warning, okay?
Okay.
So it's 45 minutes plus 10.
Okay, I will try to finish. Thank you, David. Thank you for your kind introduction. Hello, everyone. Actually, I would like to say hola todos, buenos dias. Yes, yes, my name is Junbo Zhang. I'm from NLTE, and now I'm visiting IAC. So next month, I plan to move back to China. So I feel very honored to have this chance to give a talk on my recent work before my leave. So today, I would like to talk something about high accuracy spectral modeling and chemical abundance for the oldest star. So why? Okay, so why we would like to do this? As we all know that after the Big Bang, according to the Big Bang theories, after the Big Bang, at the very beginning, every first 3 minutes, our universe only have hydrogen, helium, and very little fraction of lithium are produced. After that, then the fourth generation of stars become to be formed, and they must have the same primordial mixture of nuclei. So these population 3 stars started the reionization of the universe and created the fourth nuclear heavier than lithium. So with the time move further, more and more heavy elements are formed by nuclear fusion and the explosive death of the massive stars like supernova and the ongoing explanation of the universe. So we can see that element is a good tracer for us to explore the universe. So how we can use the element to trace to explore the origin of the star, galaxy, and the universe. Of course, we can try to determine the element abundance from the star. So determining stellar abundances is essential for us to understand the origin, evolution, and characteristics of stars, galaxy, of the universe. For example, we can derive the stellar element abundances from the sample stars by comparing them with the theoretical models. Then we can try to understand the stellar evolution. And for example, if we derive the abundance patterns for the star, then we can compare with the more theoretical models, then try to investigate the origin of the star. And for example, if we got the kinematic characteristics of the sample stars combined with the element abundance and the other stellar parameters, then we could map the whole galaxy and try to map the different population and try to explore the galaxy and the origin and evolution of the galaxy, something like that. So how to determine element abundance? One of the most important way is to use the stellar spectroscopic way. This method, how to use this method? The first thing is that we need to set the basic model assumptions. Then, according to the physical theories, we can use some equations and by a numerical analysis calculations, then we can construct model atmosphere. Then, using this model atmosphere, we can calculate the theoretical spectra by comparing with the observed spectra and the theoretical spectra. Then we can derive the abundance and the other stellar parameters. So we can see the basic model assumption is very important. So if we would like to use the spectroscopic way to determine element abundance, we usually under two assumptions. One is LTE assumptions, the other one is NLTE. LTE means local thermodynamic equilibrium. LTE is assumed that each small region of a star is in a thermodynamic equilibrium, even though the total system may not be in this state. So in LTE, the population of atoms or ions in different energy or states can be derived by solving Boltzmann and Saha equations. For NLTE, that's another way. Means the level populations are determined by the full radiation, field, and electric collisions rather than just local temperature. The population of atoms or items in different energy states can be derived by solving the equations of statistical equilibrium. Okay. I have to say that in the most cases, if you want to use a spectroscopic way to determine element abundance, LTE is enough. But in some special cases, we need to be cautious, something like that. If in the atmosphere of the star, they have very low particle density, so especially the outer part of the star, and like giants met poor, we can imagine that in such place, they must have low particle density, right? So in this case, collision rates are very low. So radiation fields will deviate from Planck distribution. In this case, NLTE analysis will be essential to obtain accurate abundance measurements. For example, in metal giants, NLTE analysis reveals that over-ionization of neutral ion and under-excitation of titanium-2, leading to more accurate abundance determinations. Ignoring NLTE, of course, you will will result in abundance error of will result in the large abundance errors. It can reach 0.2 to 0.5 DEX for critical elements. So according to my previous studies, I created a small grace of atmosphere, and I tried to explore the NLTE effects, the relationships between the NLTE effects and the stellar parameters. So we can, of course, at that time, especially for the H-bound silicon lines, we can see that for the temperature is 4,500 K and 5,500 K, we can see the NLTE corrections. You can see this is 0. If derived from 0, then the NLTE effects means will be large. So we can see the NLTE effects increase with the decreasing metallicity. And we notice that when the temperature is 5,500, when for the metal pore situation, the NLTE corrections can reach minus 0.6 DEX. That's very large. So we can imagine that if you still, in this case, you still use LTE result, then you will get a totally different result. Based on this result, you try to get some conclusion for the star, origin of star. Maybe you will get the totally wrong conclusion. So now we know that NLTE effects is very important for multiple stars and giants, something like that. So we will carry out the NLTE chemical abundance analysis for the oldest star. Why? I have mentioned that NLTE is important for this kind of star, but not only this is the other thing. I would like to say multiple stars is very important because they has been recognized as the invaluable relics of the early universe. They are usually seen as the fossil record, because their composition provides direct evidence of the nucleosynthetic process from the fourth stellar generations, and we can use these stars to probe years from population 3 progenitors to constrain the mass distributions. So how to carry out NLTE calculations for this kind of stars? Of course, first we need to construct model atmospheres, and we also need to construct model atoms. Then compare them, we can calculate the NLTE departure files. That means departure coefficients. Using these data, then we can add them into the theoretical spectra using the spectrosynthesis method I have mentioned before. Then we can derive the element abundance in NLTE. So what we have done, or what we are doing, first we need to, for Earth, model atmosphere will be have been very easy for us to get. So for us, if we would like to do NLTE calculation, we need to construct new atomic models. Jensen has constructed four kinds of element atomic models, like sodium, magnesium, potassium, and calcium. And recently, we also newly constructed the other three ones for carbon, nitrogen, and oxygen. If we got such atomic models, then we need to validate these atomic models. We usually adopted the Sun, Arcturus, Procyon as reference stars, and by combining our result using these atomic models, we can derive the element abundance. By combining our element abundance with the previous studies, we all know that these studies are well studied, right? If we can get the consistent result, then we can say our atomic models is good enough to the following calculations. So after validate our atomic models, then we can start our NLTE calculations in the sample stars. So in 2022, IACTalks has carried out calcium-2 NLTE calculation for calcium-2 infrared triplet in the very multiple stars. In his samples also include the hypermultiple stars. According to his study, they found that the triplet lines exhibit NLTE abundance corrections can exceed 0.15 DEX. That is very large, right? So now we need to validate our new carbon and oxygen atomic model in the reference stars. So this is our carbon. This is our carbon atomic model. This is oxygen atomic model. So we use this oxygen model to calculate NLTE theoretical spectra, and compare with observed spectra, try to determine the oxygen abundance from the Sun. So finally, we found that our result is consistent with the previous study, but we have noticed that for the strong oxygen 1 triplet lines, we can see even for the Sun, the NLTE effects can reach minus 0.3, nearly minus 0.3 is very large. So we should be careful using such strong oxygen lines. This is for the neutral carbon lines in the Sun. This is our result from the neutral carbon lines, and this is the result from the literature. We also derive the consistent result, but we also notice that for the optical neutral carbon lines, NLTE effects can be ignored, but for the infrared neutral carbon lines, it kind of large, can reach minus 0.25. Okay, next, this shows our calculations for Procyon. Of course, we also derive the consistent results with the literature, but we also noted that for this star, also for the infrared neutral carbon lines, the NLTE effects is very large. So now our atomic models are good, so we can move forward to the sample stars. So the stars we choose now is the primitive star J0815. This star was first discovered by David Aguado. They adopted the medium resolution spectra to determine the stellar fundamental parameters, and try to give the limits for the metallicity and carbon abundance. Later, Honey carry out the follow-up high resolution of the observation, and based on these high resolution spectra, they recalculate the stellar parameters for this star, and give the carbon and oxygen and the loss of the other elements abundance. They calculate carbon abundance based on the CH and C2 molecular lines and determine the oxygen abundance based on the neutral oxygen triplet lines. So first, we would like to see whether we have some systematic errors between different separate calculations. So we also use the same CH bonds, CH lines with Hornet's study, and we found that our carbon abundance determined from CH is consistent with Hornet's. And this is for C2. Our carbon abundance determined from C2 is also consistent with their result. But both of us have found that there is a large discrepancy from C2 and CH. Okay, this is for testing our systematic errors. We found there is no such thing. So move on to the neutral oxygen lines. We found this star is, this star is oxygen enhanced, and we found that NLTE correction for this star can reach minus 0.11 dex. But we found that our abundance is over 0.1 dex larger with Hornet's. After check, we found this may be reduced by our different normalization standard. So, and of course, the low signal to noise ratio. Okay, let's move on to neutral carbon lines. So usually for such multiple stars, neutral carbon lines is not is invisible, but this star is so carbon enhanced that it provides us a unique chance to investigate neutral carbon lines in such primitive stars. So we can see the neutral carbon lines in this star is very clear, and we can try to determine carbon abundance using these neutral carbon lines. We would like to, we can see, where is my mouse? Okay, here. We can see in the sun, we used 5 neutral carbon lines. 6 neutral carbon lines, but we also mentioned that for these infrared neutral carbon lines, NLTE effects is very large, but it's pity that for our observed spectra, this spectra is from Keck. Due to the wavelength range cannot cover the infrared region, so we cannot investigate these lines. We only include 5 neutral carbon lines in our analysis. So we got the consistent carbon abundance from neutral carbon lines and C2, but there is a large discrepancy from CH and C2. The difference can reach 0.6 dex. At the beginning, we thought this may be this may be attributed to the 3D effects, but recently, how should I say, they started carry out a detailed study on 3D effects for the CEMP stars. They mentioned that we found that we cannot attribute this to the 3D effects because 3D effects actually amplify these differences rather than eliminate them. So we cannot According to the other studies, they mentioned that maybe this is because the temperature. If you increase the stellar temperature, then you will get higher carbon abundance from CH and lower carbon abundance from neutral carbon lines. But we don't think that the change can reach 0.6 dex. So what's the true reason? Actually, till now we cannot get the confirmed conclusion. So we need more discussion about that. So this figure show that we try to plot put the most 15 most mature stars in the carbon over iron and metallicity panel, and the dot lines black dots show the predict by the supernova models. So these are the theoretical results. And if we zoom this part, we can see lots of result. I mean, for the mature stars we have found can fit the theoretical models well, but our one, we cannot use the current model to explain its origin. And in our analysis, we would like to use the neutral NLTE, the NLTE carbon abundance from neutral carbon lines. So if considering this, we would like to move the carbon abundance from CH lines to here. So we can see this star will be the most carbon rich star till now. So some works tend to put this star think this star is between the low and high carbon abundance, but we would like to say this star in a high carbon bonds. According to the recent result by Lee, and they proposed there are another high carbon bonds. They named it as population 4. It's pity that in their sample there are no mature stars with metallicity lower than -4.5. But our stars with metallicity around -5.5 here. So actually, we would like to say maybe there is another population with mature stars, especially for hypermature, with higher carbon abundance, maybe a new population. So the unique high carbon abundance will certainly shed light on the early chemical evolution of the galaxy and the nature of the first star. Okay, above that, I just mentioned the NLTE calculation for the sample star, individual stars. Actually, we would like to do more. So we are constructing the high accuracy spectral library. We know that there are lots of, with the technology developed, lots of low resolution spectra won't be satisfies our need. So lots of high resolutions spectral surveys has studied. So this figure shows lots of spectral surveys in the past, present, and in the future. For the high resolution spectra, we can see now we have APOGEE, GALAH, And in the future, we will have foremost and wave. And for APOGEE, actually, Methalos recently have published the recent results on APOGEE spectral survey. In these figures, they show the abundances of giants in the solar neighborhoods with solar metallicity in the solar neighborhood with the solar metallicity samples. We can see that for the aluminum, they are very complex behavior. So they also admit that maybe this is due to the lack of NLT corrections. Then it shows more complicated appearance. So we would like to carry out NLT calculation for more stars, and especially for the spectral survey. So first thing, we need to construct a spectral library in NLTE. So now we have calculate 32,151 spectral NLTE spectral, and including 4 elements in NLTE. I have mentioned that based on Yerson's results, sodium, magnesium, calcium, and potassium and calcium. And the wavelength range is from 2000 angstrom to 3 micrometers. The resolution is very high, but we can, according to the survey demand, to get different resolution from low resolution to high resolution. This is the parameters range, space range. So this is the temperature and log G panel, and the isochron overlaid on this finger. Now, we are carry out some text on the 4 elements. For example, for sodium neutral sodium lines, we can see the blue one is LTE spectral lines, and the red one is the NLT spectral lines. And if we let NLTE divide LTE, then we can get the NLT and LTE ratio. See, like this. If it is over than 1, then we can see the over than 1 or less than 1, then we can see the NLT effects. So we can see lots of neutral carbon lines has large NLT effects. So I have tried to plot NLT over LT ratio in temperature and wavelength panel. We can see with lots of lines. They show the NLT corrections. Okay, next plan. Of course, we need to construct more new atomic models. Now we have 7 atomic models. Next, maybe we will add more, like aluminum, iron, and so on, and try to explore the NLT abundance for key elements for more multiple stars. Then realize the determination of NLT abundance using a pipeline for large-scale spectroscopic surveys. And COROS is coming, provide us more chances to test modelings and achieve precise chemical abundance determinations. So you may ask, what is COROS, right? Okay, As one of the chorus science team member and one of the project management team member, I would very happy to give a quick introduction on chorus. Chorus is means the Canary hybrid optical high-resolution ultra-stable spectrograph. It is a next generation spectrograph that is being designed and built by multiple institutes in China and Spain, including NLC, NLTE, IAC, and GTC. It is expected that chorus will be one of the most powerful scientific instruments for obtaining precise radio velocity measurements in the world. Its capability of providing long-term radio velocity precise of 10 centimeters per second. So now it has two science. It has two science drivers. One is for exoplanets. The other one is for stars. Okay. So now we have collected and established our science working groups, exoplanet sub-working group, and the star sub-working groups. And each working groups we have three small working groups for the exoplanet. The first one is blind survey. The second one is target survey. The third one is exoplanet atmosphere. For the star working groups, the first one is for star, especially for the primitive stars. And the next one is origin of the chemical abundance, chemical element. And the next one is ultra high precision abundance. So everyone are welcome to our science working group. If you are interested in this instrument and if you're interested in this science, so don't hesitate to contact us. So David has mentioned that I'm a staff astronomer in Signal Observatory at NLTE. Yes, I have working in this Signal Observatory for more than 10 years, maybe from my PhD. I started in LAMOST. You can see the LAMOST telescope. I worked in LAMOST group, so every month I will travel to this observatory, and till now, I have to say that it's a nice experience working in this observatory. One day, if you will travel to China, if you would like to visit this observatory, please let me know. Okay, that's all. Thank you for your attention.
Thank you, Junbo. Very, very nice. Questions?
Thank you, Junbo, for this very interesting talk. I wonder, in the case that this particular star, the primitive star that we are still investigating, I wonder if this lack of agreement between the different indicators of carbon abundance, so the molecules and the atomic neutron atomic line. I wonder if there is a mixture of processes that are happening at the same time, and the fact, for instance, that the people doing the 3D modeling, they are using normal carbon abundances for those models at metallicity -3, for instance. They are not including the high carbon abundance in the atmosphere that is, to me, is changing the molecular equilibrium inside the atmosphere. So, so the fact that you have to combine CH, so carbon with hydrogen, and then to form the CH, and then the two carbons to form the C2, and also how this is interacting with the possibility to create CO and the fact that the O is interacting with hydrogen to form OH. So there are many combinations there that are happening, and the fact that this star has a huge amount of carbon, nitrogen, and oxygen at a very low metallicity. And then how this is interacting with the fact that we are not able to do full 3D non-LTE calculations of molecules so far. So I think there is still a discrepancy. People is trying to do the full 3D for the neutron carbon or neutron elements. So full 3D meaning full 3D non-LTE calculations. But I am not sure if this is just a comment. I'm not sure how. I have to check this Eitner paper to see how they are approaching this problem. But I think there are several assumptions here that are not really the real model that we have to do. And this is because the difficulties in computing everything at the same time.
Yes. Thank you, Hong. This paper actually, before this paper, we also we always think that this may be caused by the 3D effects, because the now available 3D models cannot reach such metaphor, like they can only down to -3, cannot down to -5.5. But this paper, they can down to -5, very low. So according, I cannot remember that. I remember that maybe they have at the carbon abundance, enhanced in the model. Later I will check it. But when I read through that paper, I thought, oh, it seemed the 3D effects doesn't work. But you mentioned that maybe the full 3D NLT models can help us.
Yeah, when I also had a paper in 2010 showing the effect of the 3D on OH at the very metal poor stars. So showing how the chemical evolution is changing when you include the 3D. And at that paper, we were only using the 3D LTE. And as you know, as you show, the 3D effects are providing lower temperatures in the upper layers of the star. So this means that the molecules tend to form at at higher altitudes in the atmosphere, and this is causing that the lines are getting stronger. So the correction is getting stronger. So the fact is that this was done in only LTE, and then there was some papers that were arguing that when including 3D non-LTE, you were changing again this huge effect to a lower effect. So so I don't know what is but to me, you said that they were using the model with -5. When I was working in 2010, I was working in a team in Paris where we were computing the 3D models. We had one person there that was able to compute the 3D models.
Yes.
We were seeing that the model was changing significantly when you were going from solar abundance to -1, -2, -3. Below -3, there was no significant changes, and at the same time, it was difficult to get the model converge. So the model computation, the 3D hydrodynamical model was difficult to do at these low metallicities, and that's why we were always stopping at -2.
Yes.
Going below was difficult for the computation and solving all the equations that you have to do for both hydrodynamics and then the relative transfer. So yeah, so then I doubt that this item, I have to check it, but I doubt that they are probably using carbon abundance typically that we used to assume in the halo, so maybe 0.4 4 if they are assuming that they are enhancing alpha elements, or as if they are also solar light, so C
Yes.
over iron equal to 0. But then this star has 4 decks of difference, so this is a lot. It almost has the same abundance that the Sun, being a star with a metallicity -5 or almost -6. This is crazy. So I think we need to do more into the theory of this kind of to analyze these very primitive stars.
Yes, thank you.
More questions? I'm just wondering, you mentioned your high quality spectral library, and I realized that it goes down to metallicity -2. Why don't you go for even lower metallicity?
The same. I'm afraid the model cannot to convert, especially for some situations. Actually, for the metaphor, -2.5 is a common. We just focused on the how should I say, the most common stellar parameters. Yes, for the survey, not focus on the. Actually, we can enlarge our calculation. Yes, of course.
And a more general question, Junbo. Now we are studying the chemistry of the halo, and we saw several studies showing chemical trends. And in many of the studies we are finding, they use LTE 1D approach.
Yes.
And then at the end, we are comparing the chemical evolution of different systems using different approaches. And then you can barely, interpret the results of one stream, one globular cluster, or dwarf galaxy. So as an expert on the field, what do you think we can do in order to really compare apples with apples?
Okay. In my opinion, if of course the very important thing is you can use the consistent method to derive the how should I say, the result, for example, abundance from the samples. But sometimes maybe different groups use different method. If you would like to use, then you need to scale, right? So I think for us, we can provide a consistent, comprehensive grades, and everyone can use. And I forgot to mention that once the spectral library been finished, it will be public and to everyone. So all of you can use them directly. Yes.
That would be great.
Yes.
Cool. Any other question? Aníbal.
Thanks for the nice presentation. Can you clarify what model atmospheres do you use and what line list do you use for C2 and CH, for example?
Okay. How should I say? The first question is for the
Model atmospheres.
model atmosphere. Now we
Using
use
Mars
Atlas 9.
or what kind of model atmosphere?
Use Atlas 9 model atmospheres. And for the molecular line list, we use the NIST. We download the line list from NIST.
Yes, but do you know, for example, if the C2 line list is from the one from Yurchenko, from the ExoMol?
Actually, you mentioned the other molecular line list, right?
The CH one, for example?
Yes,
Where is coming?
yeah, I have except the molecular line list from CH line list from NIST. We also has the other two molecular line lists. I didn't use the other molecular line list to calculate carbon abundance, but when I try to calculate the isotopic at the beginning, I would like to investigate the carbon 12 over carbon 13 ratio. I have compared the three CH and C2 molecular lines. Actually, I didn't see very clear differences. Only for some small region, they have some difference, but no large differences.
Okay, I just wonder if, if just, the model atmospheres, if they are Atlas versus Marx, for example, or even the line list, could even, before thinking in 3D effects, I was thinking in this kind of sense, the model atmospheres that you are using or the line list that you are using, especially for C2 and CH.
Okay.
There are very recent, very good line lists for C2, for example. For CH, I think that Thomas Masseron did a very good one some years ago.
Yes, I cannot actually I can show no, there is no need. I have used the other two start with M and Masseron and whole I cannot remember, but I'm sure I have passed the two CH molecular analysis. Yes.
I think that, for example, Marx is doing the molecular equilibrium and the opacities, especially for carbon-rich atmospheres, very well. I have worked, for example, in very carbon-rich stars like Alcor stars, and they usually do a very good job.
Yes, thank you.
Last question. Otherwise, let's thank Junbo again.
Thank you. Thank you.
Okay, this is the last seminar of the year, so let's meet back in January. And if the PhD students, you want to come and we check that I wrote down your attendance. Thank you.
Thank you.
Yeah, what you said, the problem of